Hello, everybody. This is Todd Hoff. I am your instructor for your Introductory Statistics course. We're looking to start week one material here. Week one is just kind of an overview of basic statistical concepts, what statistics means, how it's all done, and then some of the basic vocabulary. One of the things with statistics that you'll find is there are a lot of words in statistics that we see in everyday language, but they're used in a very specialized way in statistics. So one of the first parts of any statistics course is learning the language, very similar to learning a foreign language. And then just getting used to the thought processes. And this textbook starts out mostly with those thought processes in section 1. So to take a look at chapter 1 here, we are looking at Introduction to Statistics. We're going to be looking at three main things. Basically, what is critical thinking and statistical thinking, and some of the vocabulary that goes with that. Types of data. Data is what we're trying to collect and what we use to learn. And how do we collect that data? What are proper techniques to make sure that it is collected properly and we have reliable data that we can use for other things? So our key concept here, the process involved in conducting any statistical study consists of what this textbook uses as a prepare, analyze, and conclude kind of a flow chart. So this process involves critical thinking and the ability to make sense out of the data and the statistical process. So it's not just gathering a bunch of numbers and doing calculations and displaying it. There's a very set process that has to be followed to make sure that we collect reliable data and we have a problem that can be addressed. So first of all, what is data? Data is a collection of observations such as measurements. Any measurements are the big one, any sort of responses to a survey, and any sort of an observation that is taken in. Gender could be a piece of data. On every job application, you have that question. Age can be a piece of data. And as we go through the course, we'll look at different types of data and how that is all classified and how it is collected. So statistics. Now this is statistics, and I should specify here as a field of study. Because there is a statistic as another meaning. So statistics is just the science of creating experiments or studies, gathering and organizing data, and then summarizing that data and using it to make some sort of educated conclusion. We look at companies that say we make data-based decisions. That is using statistical processes. So population. Now this is very important. The population is the complete collection of all measurements and data being considered. Now some textbooks will word this as a population is the complete collection of all items that we want to learn about. And so those two definitions kind of merge together, but it's the whole group. And typically it's what we want to make it's the group that we want to make a decision or some sort of conclusion about. But we have to be careful because it can be difficult to define a population. A lot of people blow this off as being simple, but let's say we're looking at a study and we want to predict the winner of the next city election. And to keep it simple, we have candidates A and candidates B. We might look at the population and say, if I ask you to define the population, you might say, well, A and B, that's the population. We want to learn about those candidates because we want to learn which one's going to win. That is not true. Yes, we want to learn which one of those two candidates is going to win, but that's not their behavior that determines that result. The population here, you might think, well, what about voters? Yes, voters are a part of the population. But really, we only care about, to be more specific, voters who will vote in the election. If they're not going to vote in the election, we don't care because they're not going to determine the winner. If they don't vote, they have no say in the matter. So it's only those voters who are going to vote in the election. Now, if we're doing this even 2 weeks before the election, trying to predict the winner, the difficulty here is defining who's really in that population, because there might be people who say, yes, I'm definitely going to vote, and okay, we include them in that population, but the day comes and maybe they get a flat tire on their car, or an emergency comes up at work or with their kids. Something comes up and they don't make it in to vote. Well, we included them in the population, but they really weren't in it. And the other way around is possible too. Someone says, nope, I don't care about this election. I'm not wasting my time to go in and vote. But then something happens before election day that gets them wound up, and they decide that they're going to make their voice heard, and they go vote. Again, we didn't include them in the population, but they should have been. So that population can be very tricky to define at times. So a census is then collecting data, or attempting to collect data at least, from every member of the population. Our U.S. government does a census every 10 years to try to learn about the U.S. population. We have never successfully done it because we have never successfully collected data from every person in the country. There's always a few that slip through and we can't get information from. So it's not a true census, it's an attempted census in that situation. Now, something that I'm going to add here is the word parameter. A parameter is information, I'm going to write that a little neater, is information about the population. Now, there's a lot of information describing our population. We might look at our previous example of the election. We know they're all over 18 because they're eligible to vote. They reside in the city or in the voting district, so they're eligible to vote there. There's all sorts of qualities that we could list. But typically, what we're looking at is one particular parameter, which is called the parameter of interest, which describes the population in terms of what we're trying to learn. So in this case, that would have been who they're going to vote for, or what percentage of the population is going to vote for which candidate. So then a sample is a sub-collection, or a smaller group selected out of that population, and that is the group that we're actually going to gather data from. Now, a survey is the equivalent of a census, but it's from a population. Or not from a sample, I should say. We're going to collect data from a sample. And then just like we had parameters describing the population, statistics describe the sample. So one of the goals of collecting a good sample is to make sure that the sample statistics are very, very close to the population parameters. We talked about estimating and drawing conclusions. One of the main conclusions we want to draw is we want to estimate the population parameters using those sample statistics. So here's an example. Watch what you post online. In a survey of 410 human resource professionals, 148 of them said that job candidates were disqualified because of information found on social media postings. So that's important. 148 out of 410 human resource professionals surveyed admitted that they used that information to disqualify candidates. So that 148 out of 410, that is a statistic. It describes our sample. So in this case, the population was all human resources professionals. The sample was the 410 who we surveyed. The objective was to use this sample as a basis for drawing conclusions about the population. So we had 148 out of 410. We would calculate that percentage and then extrapolate that to the population. So we might say here, 148 divided by 410 is 0.36 or 36%. So we might claim if we feel this was a reliable survey or reliable sample, we might say that, hey, approximately 36% of human resources professionals will use social media to check out candidates or disqualify candidates. So now to our process. This is our critical thinking process here. And the first step is prepare. As we look through this, as we're going to prepare, we need to find the context of what we're trying to study. And I would actually say the second one here should come first. We need to determine what is the goal of this study. The example we used earlier, the goal was to try to predict who's going to win the election. Once we have decided on that goal, then we go back and look at what do the data represent. What data do we need, and what does that data need to represent for us to accomplish that goal? Then we need to look at the source of the data. Are the data from a source with any sort of special interests that might change, that make it unreliable, skew it in one direction or another? Was it obtained correctly? Things like that, and we'll talk about that in a little bit. And were the data collected in a way that is unbiased? Did we exclude part of the population, or did we only draw data from a certain portion of the population? Or were the survey, the questions set up in a certain way that might influence the way that people answered those questions? Analyze. Now, we'll look at these more in sections 2 and 3 of chapter 1, but it's basically gathering the data, organizing it, summarizing it, putting it into graphs, getting the statistical measurements, mean, median, mode, all that stuff, and then figuring out what we're going to do with it, and then finally conclude, now that we have all this data gathered and analyzed, what can we use it to say about the purpose, the question that we were asking in the first place? So we're going to focus for now on this step of prepare. So an example we're going to use here is we want to predict, can you predict the height of a person? And we're going to go with males here just because there's variation from male to female. Can you use the size of a shoe print to predict the height of a person? So here we randomly selected 8 males, and from each of them we took the length from the back of their heel to the tip of their longest toe in their shoe, and then their height, and we use that to predict, can we predict their height from their size of their shoe print? This came originally from crime scene investigation. If they found shoe prints in the yard or on a carpet or whatever, can they predict the height of a suspect based on the size of that shoe print? One assumption that is being made here, of course, is that the shoes fit. Not to tip you off, but if you're going to rob a place and you're worried about leaving behind shoe prints, buy a pair of shoes that are drastically oversized for you, and they might predict that you're taller than you actually are. I'm not saying you should do that, but that would throw this data off. If people were not wearing shoes that fit their feet well, then this is a senseless prediction. So let's consider the source of the data here. In this case, we have the table up above. We chose the sample and we took the measurements from them. Our sampling method was, in this case, the individuals were randomly selected. We'll talk more about random selection and how that is done well coming up. There are processes that are random that are still biased, that are still not going to give us true data. In this case, from what we know, it appears to be sound. Now, some possible sample issues. In this first one, voluntary response sample, there's an element of this in every statistical study, and there's just no way to completely eliminate it. Voluntary response is when, or self-selection it's sometimes called, is when people can choose whether or not to respond to the survey. Well, this is pretty much always the case. Very seldom do you have the ability to force somebody to respond, unless they're an inmate or whatever. And actually, the U.S. Census, it is illegal not to respond to the U.S. Census. Even with that, we still get people every time that it comes around, every 10 years, we still get people that don't respond. So you can't force people to respond. So there's always going to be some element of voluntary response or self-selected sampling. Now, there can be a slight difference between voluntary and self-selected. Self-selected is more, you put the sample out there online and people see it and they say, oh, I want to, or this survey, I should say, and they see that survey and say, oh, yes, I want to respond to that. So they click it and they respond. Voluntary response is more, you select the people you're going to send the survey to, but you can't force them to respond. So they still have to volunteer to respond to that survey. And generally, voluntary response surveys get less than 30% response. If you get more than 40%, that's considered very good. To be reliable, a lot of people say that 40 to 50% range. So voluntary response sampling. So the following types of polls are common examples where voluntary response samples occur. By their nature, they're flawed because you can make conclusions about the population. There are properties of the people that are going to volunteer to respond that might make their opinions different from the whole population. So internet polls. This is a case where people see it online and they can choose whether to respond. Again, there might be a quality that the people that choose to respond that share, something about their beliefs that stimulate them to respond to that survey. And so people share that belief that stimulates them to respond. Therefore, their responses are going to be more skewed towards that particular belief. We don't want to lock into that. Mail-in polls. These are even worse as far as response rates because people actually have to go through the trouble of addressing the envelope or coming up with the pre-addressed envelope and getting it in the mail. Usually very low response rates. And again, there has to be something about the topic of the survey that interests the person responding or they're not going to respond. And if there's something that interests them, there's chances are that they fall into a certain set of beliefs that are going to influence their responses. Telephone polls, same type of thing. It can even depend on when you perform them. If you're performing them in the middle of the day when many people are at work, you're only going to collect people that are not working in the middle of the day. So there's all sorts of things that can be done with those that could skew your data. So then more voluntary response sampling. The ABC television show Nightline asked viewers to call with their opinion about whether the United Nations headquarters should remain in the United States. This has been a hot topic about 10 years ago. Wanted the UN to leave the United States and go somewhere else. Viewers then decided themselves whether to call in. So they put the subject up on the screen and they said, hey, call in if you want to do a survey on this topic. 67% of the 186,000 respondents said the United Nations should be moved out of the United States. So 186,000 respondents, that's a pretty large sample size. So nobody can argue that that's too small of a sample. 67% said they should move. That's over 120,000 people. You might say, well, that's a pretty reliable result. But a separate study was done where 500 respondents were randomly selected and surveyed. So they didn't get to just decide they wanted to be in the survey. They were randomly selected. And we'll assume we forced a response here, that they all responded. 38% of that group wanted the United Nations to move. So we can see drastically different results here. We can only assume that those that wanted the United Nations to move out of the U.S. were much more emotional about this. So when they saw that survey come up or that question come up on the TV screen, they were just more inclined to respond to that survey. So because of those drastically different results, the first survey was voluntary response, where you saw that the survey was put out there and you decide you want to respond to it. You tend to get people that have a strong opinion in one direction or another that respond, are the only ones that respond. So the next step, we want to analyze data. So as we look to analyze data, there are a lot of things we can do. We can graph the data and look for certain patterns. And this is the first step that should be taken anytime we collect data, to graph the data to make sure it is a proper data distribution. And we'll talk about what those distributions should look like later on. One of the big things is we need to verify that the data can be assumed to be relatively close to normally distributed, which is one of our requirements for most of our analytical methods throughout this course. And then apply an appropriate statistical method. Does it require, most statistical methods don't require a lot of math computation. I think statistics is thrown into the math curriculum because there is some calculation and it involves dealing with numbers. But it's less about calculation and it's more about critical thinking, selecting the correct process, and then following that process, that method. So it's not intense calculation, but the real tough part in statistics is figuring out what process does this data in this situation fit into. And then the conclude side of it is to come up with statistical significance. Do we have a statistically significant result? And all statistical significance means is, with our data set and our numbers, is our result that we got here far enough away from the norm for that data set to be considered statistically significant? Now, if the data itself is very, very tightly packed together, we can get a sample result that's not very far away from it, and that could be a statistically significant result because it's on the far end of our assumed data distribution. But is that practically significant? And we'll explore that as we look through here. Statistically significant, the example they're using here is births. If we get 98 female births out of 100 randomly selected births, that is statistically significant because that is an extreme outcome to one side or another. We would expect 50-50, 50%, or 50 boys, 50 girls. If we get 98 female births out of 100, that is very unexpected. If it truly was 50-50, that would be a very, very unlikely result to get 98 out of 100. So because it's unlikely, that is statistically significant. That is one of the other definitions of statistically significant, is getting a result that is unlikely to happen if there's assumed to be no effect. The second example, 52 females out of 100 births, that's not significantly significant because we expect to get 50 female, 50 male out of 100. So if we get 52, that's really close to what would normally be just random selection. So that's no statistical significance there. Now, practical significance is not necessarily statistical significance. Practical significance, we might be looking at, is this enough of a difference to influence a consumer's decision making? So you might be looking at a price of a product. If you're looking at a new shampoo, if the price of shampoo on the market has an average price of $12 a bottle, and the new shampoo, it comes in at $10 a bottle. Well, depending on how wide of a range there is in that sample that we use to establish that average, $10 a bottle might be outside of the normal range of data or far enough to one side of it that we say that that's statistically significant. But in practical significance, many people might look at that and say, for $2, I'm going to stick with my shampoo that I really like. It's not practically significant. It's not a big enough difference to make me change my behavior. One of the examples used in the book that we'll use here is weight loss programs. 21 subjects on an Atkins program lost an average of 2.1 kilograms or 4.6 pounds in 1 year. That doesn't sound like a lot in a year, but compared to the control group, which was not on any specialized diet, that was a significant weight loss. The control group showed no weight loss or very little weight loss, so that 4.6 pounds was a significant difference. However, people that are looking to go on a diet, if you present this information, if you tell someone you could lose 4.6 pounds in a year, most of them are going to say that is just not enough of weight loss to make it worth the effort to go on that specialized diet. So as we analyze data, there are a lot of potential pitfalls. One of them we just looked at, statistical significance versus practical significance. It could be statistically significant, but it just doesn't work in real life. We could have misleading conclusions. So misleading conclusions are when we form a conclusion based on an analysis. You need to make the statement very clear what it means, I always tell people I have this problem dealing with studies that in different jobs I've had. They gather data and present it, but they don't say anything about how the data was gathered or organized. Disclosing how it was gathered or organized allows the person reading the results of the study to decide for themselves if this data is really reliable or if it was collected in a way that was misleading. The sample data may be reported instead of measured. So this is an issue that comes up as well. If I were to ask a person how much they weigh, most people are going to fudge it a little bit. They might give themselves 10, 15, 20 pounds in their own favor. So, it depends on whether I measure my weight in the morning or the evening. For myself, even, it can make a difference of 8 or 10 pounds from time of day. I'm probably going to report the lower one of those numbers, not the higher one. So if you ask people to report a number, they're more likely to give you the number that they wish it was or what they hope they want it to be rather than what it actually is. So it's always better to actually measure the data. If you want people's weights, put them on a scale and measure their weight. Loaded questions. I run into this all the time, wording the question in such a way that, you feel like you have to answer. This might be, are you in favor of increased property taxes to increase school funding? Well, the first thing you hear there is increased property taxes, and most people already have thought no. They're not even hearing the second part. If you word it in such a way, in order to be able to afford better lunches for our children at school, would you be willing to pay a few dollars more in property taxes? Well, here, the first part of the question said, are you in favor of better lunches for your kids? A lot of people are going to say, of course, we want our kids to eat well. So the way you word the question can have a drastic effect on the results. So that's one thing that's done in a lot of control studies is they word the questions in different ways and they see if there's differences among those results. And then they go back and try to find the wording that seems to be the most neutral, that doesn't affect the answers to the questions. The order of the questions. Some surveys can be unintentionally biased by asking a certain question after another. First of all, it shows, the first one or two questions have to draw their interest in. So they might be fluff questions that are put out there that you're not actually going to analyze anything on. But also, the last questions, after you ask 6 or 7 questions, they're probably not listening very well anymore. So you need to keep the number of questions down so that you have their attention for the full time. As you're going through them, you don't want to ask a question about, hey, do you want to pay more in taxes? And then turn around and say, well, how about funding school lunches? Well, if they just said, I don't want to pay more in taxes, they feel like they have to stick to that consistent answer of, no, we can't spend more on lunches because I already said I don't want to pay more in taxes. Things like that. Or a question that might elicit an emotion in the person being surveyed. And so then the next question, that emotion is involved in their answer. So some potential pitfalls, as we saw, non-response. So people that just say, I don't care enough to respond. I'm refusing to respond to the survey, or they're just not available. Low response rates. Again, there's an argument as to what constitutes a low response rate. Statistically, most people would say anything less than 40 or 50% is too low. Chances are if you're getting lower than that, you're only getting people that have strong opinions in a certain direction, so that's going to influence their responses. Some Gallup polls claim that they get less than 10% response, but they seem to claim that they have a good accuracy. It's up to those that judge. And then percentages. Some studies have misleading percentage. One thing to note, and in the textbook, it goes over a little bit if you look through some of the textbook materials, 100% is the whole thing. So someone says we've decreased your utility costs by 150%. Well, that's impossible. Decreasing your costs by 100% would mean we took it down to 0. So we can't decrease it by 150%. So that calculation had to be done in such a way as to be misleading. So that is all for section 1. We'll be back in a second with section 2. So as we venture into section 2, we're going to be talking about types of data. So we mentioned data is the information we collect from our population. Our key concept here is understanding the meaning of terms, statistics, and parameters. We mentioned those earlier. So they both describe the data sets. One's a population, one is a sample. The parameter is a measurement describing a characteristic of the population. And a statistic is a measurement or an observation describing a characteristic of a sample. And remember, we said the purpose was to select our data in such a way that our statistics very closely resemble those parameters. The problem is we never know because we don't know what the parameters are. If we knew what the parameters are, there would be no reason to select a sample and calculate the statistics. The whole purpose of selecting a sample is trying to estimate those parameters so that we can make decisions based upon those estimates. Types of data then, if we're looking at quantitative data or sometimes called numerical data, these are data where the results are numbers. So in every study, whether it's a survey or an experiment, we're asking a question. The data is the answer to that question. If the answer to that question is a number, that is a quantitative variable giving us quantitative data. We have weights of supermodels. Now, one thing to note there, that is a measured value. So that is one type of numerical data, quantitative data. Second, the ages of respondents. That's not measured, that's counted. When you ask for age, what you're really asking is how many birthdays have you celebrated? You can count those birthdays. So that is another type of numerical variable. Categorical data then is data where the response to that question puts you in a category. It might ask you, what state do you live in? Well, that state is a category you're going to be put into. Or what's your favorite color? That's going to put you in a category of people who chose that color. Gender is a categorical or qualitative piece of information. Any yes or no question is categorical or qualitative. So as we work with quantitative data, so that's our numerical data, we need to look at distinguishing between discrete and continuous. And we hinted at that earlier with the measured and counted. So discrete data is when the data values, or quantitative numerical data values, are finite. In other words, they're countable. This might be how many cars do you own? How many classes are you taking? How many children do you have? These are things that would be counted. Or if you toss a coin 100 times, how many times does it come up tails? That's something you would count. That is a discrete numerical variable. Continuous are variables that are measured. So this is height. How tall are you? We measure that with a tape measure or a ruler. How much do you weigh? We measure that with a scale. Now, I might say, well, we can still count the number of inches. Yes, but we had to decide that we were only going to measure to the nearest inch. There's no natural rounding. We have to arbitrarily choose our rounding. So arbitrary rounding. If we choose we're only going to measure to the nearest inch for your height, well, we arbitrarily chose that. Well, we could measure down to a smaller increment. Where money, that's the one that's kind of always falls in between, because money can be calculated down to a millionth of a penny. But there's a natural rounding there to round to the nearest penny. So it could be argued that money is discrete because there's a natural rounding that causes you to actually round to the nearest penny so you can count the pennies. Levels of measurement now. Once within each of these types of measurement, there are different levels. We'll start talking about each of those now. First of all, nominal. Nominal is typically for categorical or qualitative data, and it's simply by name only. Yes or no are categorical or nominal variables. There's no way of arranging them in order from least to greatest or anything like that, or preferred to not preferred. Favorite color would be another nominal variable. There is no order of better to worse. Ordinal, there's still no numerical value. Ordinal is still a qualitative variable or categorical variable, but we can put them in order. Your class grades, A, B, C, D, or F, we can put those in order. A is definitely better than a B, but how much better, there isn't really a logical thing there. Or if you're ordering sizes, small, medium, large, extra large, those are ordinal. One's bigger, but there is no set of how much bigger one is than the other. Interval now is getting into our numerical or quantitative variables. Interval is the distance between. An example here might be years. From 1972 to 1978 is 6 years. From 2001 to 2007, that's also 6 years. Temperatures are an interval level. From a temperature of 40 degrees Fahrenheit to 60 degrees Fahrenheit, that's a difference of 20 degrees. From negative 10 degrees Fahrenheit to 30 degrees, or not 30, to positive 10 degrees Fahrenheit, that's also a difference of 20 degrees. So the same interval. However, there is no natural 0 point. There is no spot where we say there is 0 temperature. We do have a 0 degrees Fahrenheit, but that's not an absence of heat. There is no starting point where we say, yep, this is the absolute 0 point. If you get into physics, there is an absolute 0, but you know what I mean. Our scale, our temperature scales do not allow for us to say it is twice as hot as it was before. That would bring us to ratio level of measurement. In ratio level, the 0 does indicate a significant amount. You might be looking at time it takes to do a task. If it takes one person 10 minutes and the next person takes 20 minutes, the 20-minute person did take twice as long. Or weight. Someone weighing 50 pounds versus someone weighing 150 pounds. This person weighs 3 times as much. There is a natural 0. Now, nobody weighs 0 pounds, but there is still a natural 0 in the weight. So, our summary of our different levels of measurement, nominal and ordinal are only for categorical data. Interval and ratio are for numerical data, and the big difference is ratio has a natural 0 point. So some things to worry about or things to address in statistics, and a lot of statistics courses don't talk about this, but some terms out there, big data. Big data refers to extremely large data sets that are very difficult to analyze with traditional software. So it has to be broken down and analyzed by several computers at once or reduced into such a way so that it's sorted and you only analyze a portion of the data at a time. And that brings us to data science. Data science is a science that involves in how are you going to accomplish that analysis. And what we're going to do in this course, we choose small enough samples that we can work with that data. But in reality, real life situations might produce data sets that are so large that we have to come up with more sophisticated strategies for analyzing that. It involves a combination of statistical knowledge and computer knowledge. Usually some sort of customized software is created and used for that analysis. Missing data is an issue. So when we're going to analyze a set of data, there might be values that are missing because the subject refused to respond. It is important to determine why that data is missing. If you look through, if you actually have some knowledge, ability to estimate the value, let's look at an example of income. If you're looking at annual income, you might be able to look at other information about the subject that we do know and estimate, okay, this person might be higher income, just didn't respond because they didn't have time. This person might be lower income. And if that appears to be randomly distributed, then it's not a big deal. If the missing numbers or the missing data is random, then we can just eliminate those data points and it shouldn't affect our analysis. Where it becomes a problem, however, is if the missing data is not completely random. For example, that surveying income. People with lower incomes might be less likely to respond to that because they don't want to disclose that they're below poverty line or whatever. So we need to look through, and if we look through and we have other information that predicts, well, these subjects have other characteristics that are consistent with lower income, and that seems to be kind of the prevailing effect on the missing data, well, then we can't just eliminate that data from our sample, because not having those subjects in our sample could artificially change the value of our data. If most of the people that didn't respond were lower income, we're going to come up with a value, an average that's way higher than what the true data value should be. So correcting it, like we said, if it's random, we can just delete those cases and get rid of them because it won't affect our result. If it's not random, then we have to come up with some way of accounting for it. One way is they call it imputing the values, which means we use some other method of guessing what those values are and including them in the sample. I caution against this because this is one of the practices that makes people not trust statistics, because this is something that is abused. The person performing the study has their own personal beliefs. And in many cases, you have a little bit of hope. You're kind of hoping that the results go one direction or another. So if they're gathering this data and they get to guess at some of those missing values, their own personal desire to make the data come out one direction or another might affect how they estimate those missing values. So it's very important that whoever is doing that estimating, that imputing of those values, is non-biased. Maybe someone from outside the study is called in and say, hey, can you look over this data and estimate what these missing values should be, without them even knowing what is the purpose of the study, what is the purpose of the data set. It's just, here's our data information. Can you help us fill in those missing values? Collaboration in statistics is always very important. And like we mentioned in the first section, non-response, low response, there's all sorts. In the real world, statistics is messy. And so there's a lot of things we have to do to try to get as reliable as possible, but there are always going to be issues that we run into. So leading us into our final section of chapter 1 here of week 1 material, collecting sample data. Selecting the sample and collecting the data from that sample. So the key concept here is we need to have random sampling. And there's a lot of cases where random sampling is not strong enough. We need a simple random sample. If the data is not collected in the appropriate manner, it's useless. It could be skewed in one direction or another, or it's just not collected in such a way that fits our statistical processes or analysis that we're going to try to apply to it. So the gold standard, when we're dealing with anything where we have human subjects, we have to be careful for that emotional or psychological effect. Giving someone false hope can actually affect their results. Any doctor will tell you that the first step in healing faster is believing that you're going to heal, or being in a good mood, having a positive outlook on what's going on. So this is where the placebo effect comes in. If we're doing a medical study or any sort of study where there's a treatment that's applied, especially if there's multiple treatments, one group might be doing a special diet with exercise. Another group is just doing the special diet. Well, they might not know which group they're in. Or maybe one group is doing diet and exercise with a medication that's supposed to stimulate weight loss, and the other group is just doing diet and exercise to see if that medication increases weight loss. Well, the group that's not getting the medication might think, well, I'm not going to try so hard because I'm not getting the medication. The group getting the medication that's supposed to help weight loss might say, hey, I'm getting this boost. Let's take advantage of it. I'm going to maybe exercise a little bit extra or be a little bit more careful on my diet. So in order to avoid that, they use a placebo. It is a ineffective treatment. They say pill here, but it's a treatment that has no medical effect at all. The only effect is the psychological benefit. It causes the subjects to believe that they're getting the actual treatment. So they don't know whether they're getting the actual treatment or not, so that doesn't play an effect on our results and change our results. So one of the basics of collecting data is the type of study being done. So I'm going to start with experiment. In an experiment, you randomly select the subjects, but then you also then randomly assign them to treatments. This could be a medical experiment. Assign half of the group to one medication, the other half to another. It has to be randomly assigned. Or it could be an observational study. Many times in observational studies, the conditions already exist. You have one group of patients that are already taking one medication and another group taking the other. You're just going to observe their results and compile those results. So in the experiment, like I said, we have to apply a treatment. And we select multiple treatments usually, and the experimental units or subjects receive the treatment that we randomly assign to them. Observational study, we're just measuring, we're not attempting to modify the people at all. The treatments already exist within the people. We are just measuring the results of those treatments within those groups. So our example here, ice cream and drownings. So an observational study, they conclude that ice cream causes drownings. How is this done? Well, because they look to see people that consumed ice cream before swimming had a higher rate of drownings. Well, things that this did not account for because they weren't controlled. Being an observational study, it's often difficult to control extraneous variables. We didn't see what was the actual temperature. It's much more likely to drown when it's cold out because you're more likely to cramp up. When it's really hot out, same thing. There can be a shock of jumping into the water and having that temperature change cause you to go into shock and not be able to swim. So there's other factors that could have been involved there that could not be considered in an observational study. So an experiment. To conduct an experiment, you might take one group and be given the ice cream, while the other group gets no ice cream, and then we send them out to go swimming and see if there's a difference in the rate of drowning. Now, obviously, there's a problem here. The experiment is a more reliable way of gathering data because it's more controlled conditions, but there's sometimes ethical issues here where you can't send people out to see if they're going to have a harmful effect like drowning. It's just not ethical to put people in danger. Now, on the other side, you might think, well, medical research, aren't we testing to see which medication has more people die or survive? Yes, but they already had the condition. They were already on their way to that adverse effect. We're applying conditions to see if they can limit that adverse effect or reduce it or extend the time frame or whatever. We didn't induce the condition that caused the adverse effect. So the design of experiments, it's very important that experiments may be duplicatable or replicatable. And what this means is someone else can do the experiment and get similar results. So it can't be just done under one specific circumstance. You got a result and that is held as the standard forever. It has to be repeated over and over again with simple results. So you have to have a sample size that is adequate so that you know that result's going to be the same. If you just test two people, give one an ice cream cone and the other one no ice cream cone, send them out in the lake, and the person who had the ice cream cone drowns. Again, very unethical study, but it's also too small of a sample size. We can't say that there's a difference there because one person versus one person just isn't a reliable size of sample. We need way more subjects than that. Blinding. Again, we talked about that placebo. We need that the people receiving the drug don't know whether they're getting the placebo or the real drug, or I shouldn't say the drug, the treatment. They don't know if they're receiving the real treatment or the placebo treatment. In many cases, we do double blinding where the people that are giving them the treatments don't even know. So if it is a medication study, someone else fills the little cups with the medication, and the person interacting with the patients just takes the tray of medications in and passes them out. They have no idea whether what they're passing out is the real medication or the placebo. Because it's been found if they know that it's the real medication, they might treat the subjects differently and might do things that cause the subject to recover, have a different psychological viewpoint of the situation that affects their recovery. So that's it right there, the double blinding, where the person, not only do the subjects not know, the experimenter, any experimenter interacting with the subjects does not know as well. So randomization. So we can't just bring in a bunch of subjects and say the first 100 go over here, second 100 over there. There has to be a random process assigning them to those treatments, and it has to be done in such a way that it doesn't skew the results. There's a lot of different theories, a lot of different levels of randomization that we're going to talk about. So the standard of randomization is something called a simple random sample. So the first N subjects. So N is an abbreviation that talks about the sample size. If I'm going to administer a medical treatment to 500 subjects get the treatment and 500 subjects get nothing. N is my sample size there of 500 for each sample. Simple random sample has to be selected such that every possible sample of that size has the same chance of being chosen. Now, this is different than a random sample. A random sample is a little bit weaker. All that a random sample requires is that every subject in the population has the same chance of being chosen. And you might think, well, that sounds like the same thing, but there are processes that we can do that are random, but they're not simple random. And there are cases where if you're just looking to gather data to describe a group, those random processes might be a better way of eliminating any sort of bias in our samples. But they're not simple random processes, which means they cannot be used in some of our simple statistical analyses. The simple random sample, as we'll see as we go through examples here, there's a chance that we could get a really bad simple random sample, whereas some of our processes in our other random sampling techniques help us to not necessarily eliminate, but reduce the chances of getting those really bad samples. But we need the possibility of getting a really bad sample for some of our statistical processes to be valid. The big part of a lot of our decision-making or hypothesis testing process is determining, is this just a really bad sample or is this a statistically significant result? So that we have to have the chance of those bad samples still included. So one is a convenience sample. We just use the data that's easy. Going back to our election example, if we want to choose or predict who's going to win the election, if we just walk outside and ask the next 5 people we meet who they're going to vote for, 2 of them say candidate A and 3 of them say candidate B, we cannot conclude that 60% of the population supports candidate B. That was just way too small of a sample, and it was way too easy. People that were not in our immediate area at that time had no chance of being in that sample. Remember, to be a random sample, they have to have equal chance of being in it. So a convenience sample is not random. Stratified sample. In a stratified sample, the population or the sample itself already has preset or pre-made divisions within it. Here they're looking at male and female, but it might be like in a hospital. You might have doctors, nurses, and support staff. And if you want to survey them about what they want, what they prefer for a new benefit, whether they want to have pet health insurance or employee life insurance, there might be a difference between what the doctors think and what the support staff thinks and the nurses think. So we would naturally divide them up into those subgroups or strata, and then randomly select from each group and put it all together and compare. But we've ensured that we have an equal number, a proportionate number from each group. Here, if we're using male and female as those strata, we divide the population into males and female, and then we randomly select half of our sample from the males, half of our sample from the females, and that makes our sample. So we know we've got equal gender representation in that sample. Now you might look at that and say, well, yeah, that helps us, not be biased by gender. But again, this is random because everybody has an equal chance of being in the sample, but it's not, I'm going to put SRS, a simple random sample. Because a simple random sample, it would be possible to accidentally randomly select a sample that is all females. even though that would be a skewed sample because it wouldn't represent the male portion of the population, it is a possible sample. And so the stratified sampling eliminates that possibility, which you might say makes it a more representative sample, but it's not a simple random sample, so it skews it eliminates the ability to use some of our statistical processes. Next, cluster sampling. So cluster sampling is a way of gathering a lot of data quickly. We're still dividing the population into groups, but it's not based on a common characteristic like male or female or doctor, nurse, and support staff. It's by geography or ease of collecting the data. In a college situation, this might be we randomly select whole classes. If we're going to survey students at noon, we select what whole classes that meet at that time, and we go to that classroom and we survey everybody in the classroom. So rather than selecting individual students and tracking them down, we selected a whole classroom full of students. This is still random because assuming that the class sizes are approximately equal, everybody has an equal chance of being in that sample. But again, it is not a simple random sample because a simple random sample could possibly be choosing one student from each class. That's not possible with a cluster sample. So here we're looking at like a multi-stage sampling situation. We might select a sample and then from there break it down even further. So in this case, we are looking at pollsters select a sample in different stages. Each stage might use a slightly different method. So beyond the basics of experimental design, we have the type of study being done, whether it's an experiment or observational. So an observational study, like we said, we observe, but we do not impose any treatments of ourselves. Whatever treatments exist already existed in our groups. Types of observational studies, we have a cross-sectional study. In this case, we observe it, we measure the data, we collect it at one single point in time, and that's it. A retrospective study is a study that's already happened. We're looking back into the past, looking at results that have already been collected, or looking at historical data and using it. A prospective study, sometimes called longitudinal or cohort, is where data is collected from a group. Then we wait a period of time and we collect data again to see how it's changed. This is the only one that is done over multiple points in time. Confounding. So confounding is when we fail to eliminate outside influences, where we said that we look at our group and we say we observe their characteristics, but part of the group, let's say one part of the group exercises and the other part doesn't, and we're looking at the impacts of a medication. We can't control that one part of the group exercises and one group doesn't. It's been shown that in many cases, physical fitness increases your chances of recovering from an illness. So that's a variable that's outside of our control that can affect our results. Confounding is any case where the results are affected by something we can't control. So it may look like we have a significant result where it might have just been one of those confounding issues or confounding variables that created the resulting data. So trying to control those effects of those variables, we try to do a completely randomized experimental design. So in this case, we randomly select the group that we're going to, the subjects that we're going to test, and then we randomly assign them to their groups. A randomized block design is a group of subjects that have similar characteristics, but the block, they might have different things that affect the outcome. For example, if we're doing a cancer research, we might select a bunch of patients and bring them in and say, okay, these are stage 1 patients, so we're going to put them in one group. And we're still going to randomly assign treatments to them. We're still going to divide them up into treatment A and treatment B, but we're going to keep them in that block because they're in stage 1. We're going to assume they have similar recovery chances, so we want to see the difference there. Then stage 2 patients will do the same. They go into a block of stage 2 patients, and we randomly assign treatments to those patients to see the effects. So randomized block design is a characteristic that already existed in the subjects. We use that to divide them up into groups and then randomly assign from there. That is still considered random and valid. It's just we need to see the effects consistently from patients that have similar characteristics and chances of recovering. A matched pair design. This is when we have sets of two subjects that should have reasonably be expected to have a similar reaction to a treatment. Often this is done with twins, human twins, or if we're dealing with animals, litter mates, so puppies that come from the same litter. One might be given food A, the other puppy given food B, and see who gains weight faster. Rigorously controlled design. Again, we carefully assign the subjects to different treatments, and we do everything we can to control all those variables. We enforce an exercise program, and we feed them so that they have a very regulated diet and stuff like that, trying to eliminate any of those confounding variables. Sampling errors can occur. No matter what you do, you can run up with sampling errors. We mentioned the simple random sample actually leaves into account the possibility of those sampling errors, and so that our statistical methods can analyze to account for that. A sampling error is simply any time where the properties of the sample do not accurately represent the properties of the population. In other words, the sample statistics and the population parameters are significantly different. So that's sampling error. It's impossible to completely avoid it, so we choose processes that make it as likely as possible to get a good sample. A non-sampling error is just a human error where we had some sort of intentional bias that maybe we didn't recognize it or whatever, such as the people that didn't respond. I'm looking at it and saying, we're just going to throw them out, where we should have recognized, hey, most of those people that didn't respond have high probability of being low income. We need to do something to account for that. Non-random sampling errors are just where there really are patterns in the data, but we failed to account for that in our sampling, so that ended up affecting our results. So as you can see, there's a lot of things in statistics that can make our results poor. It's almost impossible to avoid all of them. So at this stage, our main goal in collecting and selecting a sample and collecting data is to do as much as possible to reduce the chances of getting a bad sample, but we can never totally eliminate those chances. And so that's our first step as we move on to the next weeks of actually analyzing that data from there.